Welcome back, everyone. We're starting chapter 12 today. If you've made it this far, and you're in our class, then you made it through our midterm, and we are ready to start working on the back half of our course in abstract algebra. Very exciting. This chapter is very brief, and so I think there's a good shot that it all fits nicely and neatly into one little video. And we're talking about partitions and equivalence classes. These are two different mathematical concepts, but they're ultimately mathematical concepts for the same mathematical concept, if you will. Maybe a better way of saying that is they're two sides of the same coin, or two ways of explaining the same phenomenon. So without any further ado, let me tell you what these things mean, and then we can work on seeing that they're the same. So a partition, if you have a set X, maybe we should not start with typos. X is any set. A partition of X is a collection of non-empty disjoint subsets of X. Maybe we can call them like AI or something of X, whose union is all of X. Now, I understand that's a little bit dense, a lot of terminology there. So let's see if we can spell out what exactly this means. So non-empty, of course, means that there are no stupid empty sets. So like if I've got, here's X, we can chop up X into pieces, kind of like this. Right? We have the different subsets. Maybe we call these guys like A1, A2, A3, A4, A5. Non-empty just means I don't want any empty set. There's no A6 that has nothing in it because that would be pointless. So we just don't allow that to start with. Disjoint means that the intersection of any two of them is empty. And in particular, another way of saying this is if X is in AI intersect AJ, then I is actually equal to J. So here, one way of saying it is that we have I different from J, no intersection. And if something ever is in the intersection of these guys, the two of these guys, then they're the same subset to begin with. The last requirement that the union is everything is that every X in X lives in some Xi. There's no like unclaimed part of X. In other words, you could think of this as like carving up a map or sorting any kind of objects. That's actually a really good example. Whenever we're talking about partitioning a set, we're kind of implicitly thinking about sorting the elements in some capacity. So the example in Pinter's book is that if you have your coin jar at home, then you could go through it, you could spill the coins out on the table, and then the coins as a whole represent X, like the jar is X. But when I sort them into pennies, nickels, dimes, quarters, maybe you got some dollar pieces or some 50-cent pieces in there, that's fine. Well, once you've gone and sorted them all into their respective categories, then those categories are like playing the role of the AI. There's no coin, which is both a nickel and a dime. And if it somehow you had it, or you had a coin belonging to two classes, you would realize that actually those are the same class all along because all the coins are visibly and, obviously distinct classes. Okay, so that's partitions. The other side of the coin, no pun intended, is equivalence relations. And we saw these actually when we were talking about isomorphisms. I gave you a quick crash course on those because I wanted to explain to you guys that, well, isomorphisms is a kind of equivalence relation, and that's very helpful for solving problems and deciding isomorphism types of groups. It's just a useful tool. But let's remember how that works. An equivalence relation is a relation on a set with the following three properties. It is reflexive, meaning every element, let's not use the letter A, let's use X. Every X is equivalent to itself. It is symmetric, so that if A is equivalent to B, that implies that B is equivalent to A. And lastly, it is transitive. And this was the really core property that was helpful for us last time we encountered this concept, which is that if A is equivalent to B and B is equivalent to C, then A is equivalent to C directly. And this is what we were really using when we were, maybe we have two different groups, both isomorphic to B, then they're isomorphic to each other without making reference to B. Not saying that it's necessarily easy to cook up such an isomorphism or whatever, just that the concept of transitivity is that in principle, you don't need a B. So it turns out that equivalence relations and partitions are basically the same information. And so that's what we're going to spell out now in the rest of this video. An equivalence relation on X determines a partition of X, and every partition determines an equivalence relation. This is the theorem for this video, I guess. So let's work on the proof. And here's the idea. Given an equivalence relation on a set X, then what we do is we define the partition by letting square brackets X denote all the set of, how about we write X in X? I don't want to overuse the letter X. How about we say the Y's in X such that Y is equivalent to X? In other words, this thing is not the element X, it's the set of all things equivalent to X. Now, by the reflexivity part, X is equivalent to itself, and so that's a perfectly good thing to include, right? X is in square brackets X, but so are probably a bunch of other things. We're going to call this the class. Sometimes the equivalence class, if I want to be specific, but just in general, the class of X. Okay, so if I have an equivalence relation, then the classes of all the different elements in X, I claim that they're a partition. So in order to see that, we have to see that what we have done is actually divide X into a family of sets, which are non-empty and disjoint, and whose union is everything. Well, non-empty is clear because the classes come from elements, right? Every class contains itself. Sorry, every class contains the element that I'm using to notate the class. There's no way of talking about an equivalence class unless you have an element in mind. The next thing we need is the union is everything. Of course, right? Since every X in X belongs to some class, then the union over all the X's is the big set X. Of course it is, because that would be just grabbing every element at least and putting them all together. The interesting bit is disjoint. In other words, can it be that X intersect Y is non-empty when X and Y are different? And the answer is yes, that can happen. But if these things are non-empty, so if we have some Z in the class of X and the class of Y, then Z is equivalent to X and Z is equivalent to Y. And so by transitivity, these two classes are equal, right? Because they're equivalent. And so, in other words, if there's something in between them, they're equal. And otherwise, then there's nothing in there. And so this gives the definition of disjoint that I had up on the board up here, right? If there's something in the intersection, then they're the same. Otherwise, there's nothing in the intersection. So far, we have proven that equivalence classes give a partition. Now we have to do the other way around. This is partition defines an equivalence relation. I think this direction is easier. For this, what we do is we have X divided into AIs with those properties. Maybe we should cut this off here. And in order to get the equivalence relation, we define X is equivalent to Y exactly when X and Y are both in the same AI. Otherwise, X is not equivalent to Y. So in other words, the partition is determining the classes. And what I have to do is see that this satisfies the three properties. So we have reflexive. I need to see that X is equivalent to X. Is X in the same class as Y? Well, being in the same class is the same thing as being in the same partition set. And of course, every element is in the same AI as itself. For symmetric, I have to see that if X and Y are in the same AI, then Y is in the same, if Y is in the same class as X, X is in the same class as Y. Now we're really being precise about the language, but of course that's also true. Lastly is transitive, which is that if X and Y are in the same class, and Y and Z are in the same class, are X and Z in the same class? And again, this is very straightforward, right? If there's a specific AI which houses X, and we see that Y is also in there, and then I have an AJ that Y is in, that Z is also in, well, we know that I is equal to J already, and so therefore X and Z are in the same class as well. So we've done it. Equivalence classes are the same thing as partitions. And I think that might be just about everything that I wanted to say about this chapter. Maybe one kind of closing remark that stands out to me, just because I think this is a cool piece of mathematical trivia, is that it is remarkably difficult to figure out ways of counting partitions of sets with any kind of properties. Like off the top of my head, I know that it is possible to come up with a simple formula for how to divide n things into k sets. That's called stars and bars. But there are lots of famous combinatorics problems where you try to divide sets up with like any kind of additional rules than that. And maybe I don't think this is a reasonable thing for our homework because our homework is about algebra, not combinatorics. But I think maybe down the line, if we talk about some combinatorics, then this would be an interesting thing to revisit because there's a lot of cool stuff that we can talk about. But first, we should look at our practice problems for this section. So hold that thought, and I'll see you guys for practice problems in just a minute.